Hello all! So, today we're going to be looking at an introduction to some counting principles. So, we've already seen some ideas of our basic counting sorts, so like unordered list, ordered list, combination, and permutation. We'd like to work our way towards getting some formulas for these, but before we even start off on that, there's one basic counting principle that it's worth getting an understanding of that's going to help us figure out how to approach all of these different situations. So, I'd like you to think of a scenario. We've got, I don't know, whether for a game or just because we're stuck doing counting problems, we're going to roll one standard 6-sided dice, and then flip a coin. We want to know how many outcomes we've got. So one way to organize that is in a tree diagram. So if I have my possible outcomes from my dice roll, I could get 1, 2, 3, 4, 5, or 6. From that, each dice roll outcome, I'll then flip a coin. If I rolled a 1, I could get either heads or tails, likewise for 2 and all the rest of the numbers. So heads, tails there. Add in my heads, tails for each one. Heads and tails. So now I've got my tree diagram representing all possible outcomes for this dice roll and coin flip. I can count the number of possibilities, and that's going to get me 4, 6, 8, 10, 12. I want to look at ways that I can save myself some of the work of always drawing out a tree diagram. So if we notice what happened, so first I rolled my dice. There were 6 different ways that could, 6 different outcomes from that. For each of those outcomes, I was then flipping a coin. What I had gotten on my dice didn't affect what happened to my coin. And so for each of my 6 possibilities, I had 2 branches here. So we've got 6 pairs of 2 happening right here, or in other words, if I multiplied that 6 times my 2 possibilities for my coin flip, I would end up with this outcome of 12 possibilities, and we can kind of see that it makes sense to multiply. We've got our 6 different copies of 2 outcomes here, and so we can extend this as a general principle. If you're looking at counting possibilities and you make a choice and then you make another independent choice, we can look at all the different ways that we can make each choice, multiply them together, and get our outcome right here. So, as another potential example, if I were to look at, we've got an ice cream parlor, so we've got choice of cones or containers. You know, they offer maybe cup, cone, or one of those fancy chocolate dipped waffle cones. We've got our ice cream itself. I don't know, we can go with our standard vanilla, chocolate, strawberry, and then maybe they've got peach, cobbler, and I don't know, one of those moose tracks type amalgamations. We've got toppings available, like say chocolate syrup, whipped cream, cherries, and I don't know, some chopped peanuts. So the question is, how many ice cream bowls can you make with these choices? We could say, well, okay, first we choose our container. We've got three different choices there. Next we choose our ice cream itself. We've got 1, 2, 3, 4, 5 choices there. Next we choose a topping. We'll say that each ice cream container topping pairs equally well. So for each of our container and ice cream combinations, we could equally well choose any one topping. Our budget doesn't allow us more than that. So we've got 4 toppings there. If we multiply all 3 of these together, we could figure out that we've got 60 different possibilities. If we were to have constructed a tree diagram, it would have demonstrated the same thing. It just would have taken a very long time. So we've got this big idea that we can multiply, if we can break down our scenario into a few different choices, we can multiply them together to figure out the number of different outcomes. For your first exercise, so my brother and some of his friends crafted a game called Trouble Sorry. So there are 2 existing games, Trouble and Sorry. Each are about, moving pegs around a track once and getting them into your home, and then you can knock out your opponent's pegs. In the game of Trouble, you roll a dice to figure out what your move is. So for Trouble Sorry, we both have the dice roll from Trouble, the game board and cards from Sorry. You both roll 1 6-sided dice and pick a card. There are 11 choices in the game of Sorry, and then there are these complicated rules about you've got your movers on both boards, how you can use that total outcome, distribute it among everything, how everything works. But for our analysis right now, we want to say how many possible outcomes. This is a brand new game, it needs to be studied. For your roll and draw, how many different possible starting values can you have that you would need to play out on your turn? So that's exercise 1. We've got this great algorithm. It does help us analyze a lot of situations if we can break things down into these choices. There was one key word in there that might have gone unnoticed. We want these to be independent choices. So let's look quickly at another counting question. We've got the word C, and we're looking at how many ways to rearrange the letters. Into distinguishable words. So we'll go back to tree diagrams just because I'm warning you that this might not work out the way we would expect. We might say, okay, first choice, we've got our first letter, we can pick one of those. Second choice, second letter, we've used 1, we'd have 2 left, so we'd have then 3 times 2, and then the last choice, we're stuck. But let's see how this plays out. So for our first letter, we've got our 2 choices, They could either be S or E. So we've got that. Say we chose the letter S as our first letter. We've gotten rid of that S. We've got 2 E's left over, but it's the same letter twice. So we can only pick the letter E as our next letter. And then we know that the other E would be left as our final choice, so this would actually spell out the starting word C. If we chose E as our first letter, we've still got 1 E left over, and we've also got an S. So I could either pick an S or an E as my second letter. If I pick an S, I've only got an E left over, so that would be there. If I pick an E, I've got an S left over, so that's determined. So if I look at my table, I've got 3 paths, three rearrangements that actually look distinct. So my multiplication strategy didn't work. So we've got to pay attention. In our ice cream example, once we chose a type of container, we could choose whatever ice cream and topping still we wanted. Here, our first choice indicated what our second choice, I guess, what options were there for our second choice. You know, maybe another example might be if you're looking at some sort of residence life drawing, and so you pick a living unit and then you pick a room number in that unit. We might have different numbers of rooms in each unit, and so we wouldn't just be able to multiply the number of living units by some number of rooms per unit to get a final number of outcomes. So that is what I'd like you to think a little bit more about for your second exercise. Find another scenario involving 2 choices. In which the number of options for your second choice depends on the outcome of the first choice. So, thinking a little bit more about other possible scenarios where our multiplication algorithm does not work, where we need other paths through the question. Thank you for watching, and I will see you in class.